Hey guys, so this is our dynamics project. My group consists of Matt Walker, Bryson Chan, Austin Matt Miller, and me, Ahmed Gouda. So basically what our project's on is centripetal acceleration. We went to the biomechanics lab and saw that a football spirals, and with that spiral, it has a centripetal acceleration across the ball when the ball spins. So here you can see Broncos quarterback Peyton Manning throwing the ball. It's going in a good spiraling motion, and there you go. I'm going to go into a quick lesson about centripetal acceleration. As you can see, centripetal acceleration has two components, a tangential component and a normal component. Right now, Matt's going to go a little bit more into depth about centripetal acceleration.
So this dot right here represents this white piece of the charger that was traveling in a circular path at a constant speed. However, its velocity was changing. So the first thing we want to do when we're trying to find centripetal acceleration is choose a coordinate system. In this case, we're going to choose normal tangential because that allows us to find velocity towards the center of the circle and the velocity in the tangential path. So this is the normal component and this is the tangential component. And we can see the change in velocity caused by centripetal acceleration. If we look at the velocity of the charger at this point is directly to the right, and then if you imagine it right here, velocity is going to be still tangential to its path. So the change in velocity goes from head of this vector to tail of that vector, and it always points towards the center of the circle. So this vector represents our acceleration in the normal direction.
So now what we have for you is a quick quiz review question. So as you can see in the diagram, there's a boy walking towards the center of a circular platform. It's moving counterclockwise. So what we want to do is find where his tangential and centripetal acceleration would be. So in the diagram, you can see this is the positive e sub n direction and this is the positive e sub t direction. I'll give you a few seconds to answer this question. So as you can see, it is in the positive e sub t direction and the negative e sub n direction that he has acceleration. And what you would want to do is use the head to tail rule that Matt explained earlier. So here's another quiz question. So in our charger example, where Matt was moving the charger in a centripetal motion, what is providing the force causing the centripetal acceleration? A, weight of the block, B, tension in charger wire, C, drag force, or D, force of Matt's arm? I'll give you a few seconds to answer this. And in this case, it's the tension in the charge wire, B. So now we're going to go into our project example from the biomechanics lab with the football. This is a video showing how we got our data.
For our multimedia example problem, we want to use the data from our biomechanics lab to find the centripetal acceleration at the center of a football while it is spiraling through the air.
Here you see Bryson throwing the ball and it's spinning. And yeah, that's basically it, how we got our data. So this is how we got our numbers. When we visited the Human Motion Biomechanics Lab, we used markers and cameras to track the X, Y, and Z coordinates of each marker on the football at different instants in time. Then we isolated the Z-axis data and graphed it to find when the marker was at the top of the football using this graph. So the marker was on the spiral of the football. And basically, what these peaks show is when the marker was at the top, and these low points show when the ball span and was now at the bottom of the ball. So So, when the sensors reach one of its peaks, you know it's at the top of the football. That allows you to analyze the forces causing centripetal acceleration, which is at that instant the z direction only. Analyzing our data using the formula v equals ds over dt, we first found out two different velocities just before and just after the ball reached its peak, which in this case would be like these 2 points. Then we used a equals dv over dt to find the acceleration of the sensor when it was right at its peak. We knew the radius of the football, mass of the sensor, which allowed us to solve for the tangential velocity and force of the Velcro. And so that's basically the data that let us create our example problem. And now we're going to go into our example problem. So this is it. So now on to our example problem. Group 8 was testing to see how much force the Velcro on the sensor on a football could sustain before flying off. The sensor rotates around the football at a constant speed of 1.71 meters per second. The radius of the football is 82.8 millimeters and the mass of the sensor is 6 grams. If the Velcro can't sustain a force greater than 1 Newton, will the sensor fly off in this trial? What about for a speed of 0.8 meters per second? So, the first step of our process is figuring out if it's a kinetic or kinematic problem. In this case, kinetic because it relies on the forces on the system. So, the first thing we have to do is draw our free body diagram. Our free body diagram is shown below as two forces, and our two forces is our sensor's weight going downwards and the normal from the Velcro on the football onto the sensor going upwards. And our kinetic diagram is shown to the right as our acceleration in tangential direction going to the right and our acceleration in normal direction going downwards. So, our next step is figuring out what equations we want to use. So our acceleration equation in our normal tangential direction is a equal to dv over dt in the e sub t direction and vt squared over rho in the e sub n direction. In this case, our acceleration in tangential direction is 0, and our acceleration in normal direction ends up being 35.31 meters per second squared. So now that we have the acceleration in normal direction, we want to solve for our force. So we know that the forces are weight going downwards and the normal from the Velcro going upwards. And after solving for the normal of the Velcro, we get 3.6 newtons, which means in this case the sensor will fly off. Now, on to part B. In part B, our velocity is 0.8 meters per second squared. In this case, after solving, we find that the normal force from the Velcro is 0.78 newtons, which is less than 1 newton. So in this case, the sensor will not fly off. So that's our dynamics project. We hope you learned a little bit more about centripetal acceleration. Thank you very much.